Welcome to the next lecture in which we will discuss multi-carrier communication systems and principles of OFDM systems. In the previous lecture, we have seen that if the signal bandwidth B suffix S is smaller than the channel coherence bandwidth, then this leads to flat fading. Flat fading means that the complete signal will undergo a similar kind of signal degradation. If fading is allowed, then flat fading is the best option that we can have. The entire signal spectrum is then undergoing the flat fading, which is a convenient thing. But whenever this signal bandwidth is more than the coherence bandwidth, we have frequency selective bandwidths, which means that different spectrums of the signal undergoes different amount of fading in terms of amplitude attenuation and phase deterioration. Frequency selective fading introduces a large amount of distortion. So systems have been therefore built to check if BS is more than BC, which means the signal bandwidth is more than the coherence bandwidth, then can we avoid this frequency selective bandwidth. As it turns out, if BS is more than BC, we can use n total subbands where each signal will now have a bandwidth of BS upon n. Therefore, if this Bs upon n appears to be less than B suffix c, then each subband only suffers flat fading. Such systems are called multi-carrier modulation systems, in which serial data is converted into multiple parallel streams, and each parallel stream is undergoing flat fading if this criteria is met. This is the basic criteria. The bandwidth of each subcarrier is Bs upon n. In multi-carrier system, what is the basic advantage? That if we have only one signal over the complete frequency, then this is called single carrier modulation. But while we use n number of sub-channels, then they are called multi-carrier modulation. Now in the first system, if there is multipath channel fading, it impacts the complete signal once. While in multi-carrier modulation, even if there is multiple channel fading, it can impact one of those carriers, but other carriers go through. And this is the main example. The complete signal is affected at once in single carrier modulation. The effect is only on finite subcarriers, in remaining are transmitted without any distortion. The time period of each signal also increases. You can understand if we are reducing the bandwidth by Bs upon n, which means now the time period becomes n upon Bs of the new signal. Originally it was 1 upon Bs. This was the time period of the symbol. Now the new time period Ts dash is n times of Ts, and therefore the time period increases. And this also has one more advantage, that now if this time period, new time period T symbol is greater than the coherence time, the communication becomes more reliable, because we know that the channel behaves with more temporal correlation when we talk about one coherence time. So if the coherence time is less than the symbol time period, which means the complete symbol is now going under a coherence time duration, which is very good thing. So reliability increases. So it has two effects. One in frequency, it reduces Bs upon n. It also increases the time period, and therefore time period now becomes larger than the coherence time. So if there is also a bandwidth saving concept, that if we use general FDM systems, this is FDM systems, then frequencies f1 to fn, all of them, if they are separated individually by guard bands, then there is some loss of frequency. However, it is possible that we can overlap all those frequency components if they mathematically satisfy some condition, and therefore there is some bandwidth which is saved. There is some bandwidth that is saved. These carriers are orthogonal. They overlap, but still they can be sampled at particular instances, and therefore this system is called orthogonal frequency division multiplexing. Orthogonal frequency division multiplexing is a type of a multi-carrier modulation possibility. So in orthogonality, you can see I just plotted frequency versus amplitude to illustrate that there can be multiple carriers which overlap, but you can see at one sampling instant only maxima of one carrier exists. When this point exists, there is no other signal existing at this point, all other are zero. Similarly, when we sample at this instant, only this is available, at this only this is available. So we can have at different frequency points only maxima of one. All of them are overlapping, but they are orthogonal, and this is possible that we can only sample one of these multiple carriers. We can send multiple carriers By sending multiple carriers, we make Bs upon n is smaller than the coherence bandwidth and still manage to sample and retrieve our information signal. Mathematically, xt is given by components, addition of components from I is equal to 1 to n. So there are n subcarriers. This is n subcarriers, you can understand, n subcarriers, and all of them are added. Basically what happens is that there is an information symbol. So this xit is the baseband modulation. We perform PPSK suppose or FSK. So this is the information is modulated in baseband, and then it is multiplied by a carrier frequency which is FIT. FIT is basically I times of B upon n. And for each, so you can understand it will start from I starts from 1. So when I is equal to 1, we have B upon n. When I is equal to 2, we have 2B upon n. So these are the frequency components. Now this is suppose F1, then this is F2, and we will go like this till the nth instance. So we basically add the multiple sub bands to model it as a xt. What happens at the receiver? If the receiver receives this xt OFDM signal, it will also have a component of noise. So we can write that it's summation of xit and the noise component. For now, we want to illustrate what will be the condition of orthogonality, and therefore we assume that the noise component is 0. If the noise component is 0, the received signal is this. Now how do the correlator receiver receives for any passband transmission? You can understand that we multiply with cos 2 pi fct the incoming wave, and then we pass it through a low pass filter. This is the correlator receiver. So which means that RT will be, we take yt and we multiply by complex conjugate of the frequency at which we are trying to identify. So suppose I am trying to identify the zth component. Z is in between 1 to n. We have sent n subcarriers. I am concentrating to find out what happened at the z. So this will be the illustration. We will have 1 upon t integration 0 to t naught I is equal to 1 to n xi e raised to the power j 2 pi bnt. This is my OFDM received signal, and this is the correlator carrier, the carrier fz corresponding to zth carrier. So in that case, if I can modify it, I can take common e raised to the power j 2 pi I minus j p upon nt dt. Now what we want RT to be x of j. Understand this, x of j, or suppose x of L if it is. So for that to happen, we want everything else to become 1, which means this component should become 1. It will become 1. It should become 1 only when from all the n components, when I is equal to j, it should be 1, which means I can also write it as a delta I minus j, and a Kroneker's delta. It should be 0 when I is not equal to 0. And if I then integrate this 1, what will happen? It will happen 0 to t naught of 1 dt, which means it will be t naught. So it will be t naught multiplied by, I have written it xl, so just kindly take it as xz. So 1 upon t naught was in the definition. There is a t naught as integration and xz. So what you get? You get the z symbol. So which means in order to retrieve my original signal from orthogonal signals, this is the criteria that needs to be satisfied. So which signal can possibly be used? If this criteria is to be utilized, you can understand that yt was summation of this. Yt was summation I is equal to 1 to n xi e raised to the power j 2 pi I bn by t. If we take ts, what is ts? Ts is basically 1 upon fs. If I say sampling frequency, and what was my sampling frequency? It was b upon n, total bandwidth b divided by the number of subcarriers n. So if I take t is equal to ts in this equation, I will have y of ts is equal to, in this expression I will have t is equal to ts, but ts is nothing else but n upon b, and therefore you can understand that this cancels out, and what you get is summation n is equal to 1 to n x n, you can write for n e raised to the power j 2 pi n. What is this operation? You can understand there used to be a twiddle factor wn, which is e raised to the power minus j 2 pi n, and this we used in case of discrete Fourier transform. discrete Fourier transform. So if this total factor is minus sign, it is discrete Fourier transform. In this case, it is of plus sign. Here it is a positive sign, the power of complex exponential, and therefore this operation is actually an IDFT operation, very well written. And therefore, in order to maintain orthogonality in OFDM systems, we use inverse discrete Fourier transform. Also, to go further, the part of orthogonal inverse DFT that we will compute will be for large subcarriers. So a number of subcarriers will be 256, n will be 256 suppose, or it will be 512. So which means that we will have a large number of subcarriers, and therefore the IDFT or DFT operations will be performed using fast Fourier transforms. Remember, the fast Fourier transforms are nothing else but a technique to compute discrete Fourier transforms. So we will compute IDFT. So which means the transmission has to be done using IDFT to maintain orthogonality in OFDM symbols. There is one another problem that occurs in case of OFDM systems when we use this, and it is called intercarrier interference. So suppose we modeled the multipath channel in our previous example. So suppose we are discrete system we are looking at. So there is an input and an impulse response and output. What is the output? The output is basically the convolution of the input with the impulse response. So if I write like this, this will be the convolution. Now if we say that the transmitted symbol was x of 0, x of 1, x of 2 till x of n minus 1, in total there are n symbols. There are n symbols. So if I put these n symbols in this equation, what I will get, since it's a causal system, I'm not taking h of minus 1. H of minus 1 is equal to h of minus 2 will be 0 for non-realizable systems, non-causal systems. So the first term that I will get from this will be h of 0 into xn, then h of 1 xn minus 1, and h of l minus 1 n l minus 1 plus n. And if in total there are l copies. So which means you can understand that if I am writing h of 0 and it depends on x of n, this is n, this is n, and other components that I have highlighted in red are basically xn minus 1, xnl minus 1 plus 1, xn minus l plus 1. These are past symbols. Let me clarify this concept again. So suppose that x was this, x0 to n minus 1, and x1 was some previous symbol. X1 was the previous symbol. So previous symbol, the previous symbol was x1 of 0, x1 of 1, x1 of 2, and x1 of n minus 1. So if I concatenate the two, I'm taking for two time periods, so ts1 and ts2, two symbol durations. Then first of all, there is this which I have written in red. These are all x, and this is my the transmit. This is x1 and this is x. So this is the present symbol duration, and this was the past. This is the past. So if I now convolve yn as hn convolution xn, it will be this. So if I write this, you can understand it will be y of n was h of 0 x of n, h of 1 multiplied by x of n minus 1, h of l minus 1, n minus l plus 1. So if I write n is equal to 1 here, what will happen? It will be h of 0, x of 1, and what was this n minus 1 term? The n minus 1 term was from the past symbol. This was the past symbol. So this is why we are saying that this was the past symbol. Remember, this is the past. So the n minus 1 component will come from the past. Similarly, n minus l plus n components will also come from past, which means at n is equal to 1, if I want to find out the output, I want n is equal to 1 input and other past inputs, right? So in order to eliminate this, we use a concept of cyclic prefix. In cyclic prefix, we have the past, the present, and we knowingly insert some LP copies of the present because we know they are going to impact. We know that they are going to impact here. We have seen that it has impacted. So this is actually a component derived from the present symbols. These are symbols derived from present symbols, and therefore when now I write this equation, the previous equation, the past inputs will come from these LP copies, and these LP copies are called the cyclic prefix of OFDM systems, and this avoids inter-symbolic interference because these past symbols do not now tell me what the output is. The output will depend on the present symbols and the cyclic prefix, but cyclic prefix is actually derived from the present symbols. This is the concept. So in totality, what will be the block OFDM block diagram? The OFDM block diagram, we will have information signal. We'll convert serial to parallel because we want to make n subcarriers, right? So from, you can understand, from 1 to n. Then we'll perform the baseband modulation. We'll have XI, BPSK, FSK, any scheme. Then we'll perform IFFT. Why we'll perform IFFT? This is to maintain orthogonality. This is to maintain orthogonality. And then we will have to add a cyclic prefix. So if this was the past, if this is the present, then we will have cyclic prefix. We also will have to perform passband modulation, right? Because what happens in a communication channel? We also need to perform a passband modulation, which means we have to increase the frequency. First of all, this is digital at this stage, and the communication channel is analog. Therefore, we want to convert it into analog. So how do we convert a digital symbol into an analog symbol in communication systems? By performing a high carrier modulation. That is called a baseband transmission modulation. Anything, any high carrier frequency. Then we'll perform parallel to serial conversion, wireless channel. Then noise will be added. This will be the signal. Then we'll perform serial to parallel, and again high carrier demodulation. We will remove the cyclic prefix. We will perform FFT. The baseband demodulation will be performed, and parallel to serial. So this is our OFDM transmission.